Hi everyone, today we're taking the question 3534. So it's the daily question for 10th of July 2026. Now in here we are given four parameters. We have a nums array, we have maximum difference, and we have queries. So it says that for every query, we have a source and we have this destination. We have to find the minimum distance in between the nodes. And if there exists no, path, we have to return -1. Now, what is this nums array? We have a nums array and we can go from node I to node j if the absolute difference between them is less than maximum difference. So this is the question. And the trick here is, and the main thing here is in the constraints. It says that my length of array can be up until 10 to the power 5. And my query length can also go up until 10 to the power 5. So if we manually find the you see the path every time we are going to run into TLE. So let's see how are we going to solve this. So firstly, we find the query size, which means we find out how many queries we are given with. So we store that in query size. Now what we do, we have this result array. So we are going to return this result array. You see, we have to return an array answer where answer of I is the result of ith query. So then we fill it with -1. Why -1? We have to return -1 for a query if there is a no, if there no is a, like if we couldn't find a path. So that's why we've initialized this to -1. Okay. Now assume that this nums array that we've given, it's not sorted. So if we sort this, our life would be easier because then we would know if we can go to edges in nodes. We don't have to check for the entire array, which node to go next, right? So what we do is we sort this. Now let's assume you have, a pond where you have a lot of lotus flowers. So they have different heights. So you sort them on the basis of their height. Now, when we sort them, we just don't do 1, 8, 3, 4, 2. And we just don't sort this array. We don't write 1, 2, 3, 4, and 8. Why? If we do this, we are going to, lose track of the I and j values, which is node value. So along with the value of nums, we also have to store the node value, right? So this, like my index for this would be 0, 1, 2, 3, 4. So when we sort 1, which is at index 0, we have 1, 0 together. Then we have 2 at index 4. So we'll store the index as well. So this is how we sort so that we also have the node value. Same for 3. 3 was present at second index. So we have second index as well. Now 4 was present at third index. So on and so forth. So what we have done here is that we have stored the nums value for I along with I, correct? So then we have this sorted nums and we have this nums of I comma I as its value, and then we sorted based on the first, we have this lambda which says that nums of I, we have to sort this based on nums of I. That is why A of 0 and B of 0. So this is the time complexity of this sorting. Now then what we do is, now what happens is, we have this array, right? It was at first index. Now we get this, right? After sorting, we have this. But you see, there's no way, if I want to know from node 0 to node 4 directly, there's no way in this sorted array I could get it in big O of one time. So that is why we have this mapped index, which would tell us that, let's say this is my I. In my sorted array, what's my index here? It's 1. Then here it's 2. sorry, zeros, index starting from 0, 1, 2, 3, and 4. Now, there's no way I could know that my, node 0 is stored at index 0 in my sorted array. So that is why we have this mapped index. What it will do is, it will tell me that, it will say that, my index 0 is stored where? At index I. So it will tell me 0 is stored at 0. 4 is stored at 1. 2 is stored at second index in my sorted array. So this is what we do in mapped index. Fine. Now what we do is, we have this second step. We are basically pre-computing some values. So now that we have this array, what we do is we find out the connected components. So, how do we identify if we can go from one node to another node? How do we? The formula is if the absolute difference between I and j is less than maximum difference. So what we do is we have this connected components. Initially our size component ID 0. So whatever components are connected, we are going to give them the same component ID. Fine. So this is the trick. So we see if, the difference is greater than the maximum difference, we know that we have to increment the component ID. So we increment and add it here, or else the same component ID will be assigned. So this is how we go about this. We assign a component ID so that, whenever we need to know, like for example, let's say from node, can I go from 1 to 2? Yes, we can. Why? Because here, um, what's my maximum difference? 3. So in between 1 to 2, my difference is 1. So these will get assigned the component ID of 0 and 0 only. Now in here, we'll check, can we go from 2 to 3? Yes, we can. So this will also get assigned 0. Now can we go from 3 to 4? We can. So this will get assigned 0. Now from 4 to 8, can we go? No, we can't. Because the difference is 4 and a maximum difference allowed is 3. So that's why this has component ID 1. Now, whenever I need to know if there's a path in between, let's say this value and this value, we just have to check the component ID. If the component ID is different, we know that there is no path. We can't go. This is another connected component, and this is another connected component. This basically means that 0, 2, 3, and 4 are connected, and 1 is not connected. You see the graph here? So now what we do is, this is a step 3, where we basically say we have an array next jump. Now, herein we saw the connected components, right? Now, what we want to do is we want to check in one move only. Like instead of checking, can I go to 1 to, can I go from 1 to 2? I can check. I need to check in one move only. What's the maximum I can go? Fine. So, let's say from 1 to 2, am I allowed to go? Yes. From 1 to 3, the difference is 2. I can go. Can I go from 1 to 4? The difference is 4 minus 1, 3. Now 3 is less than equal to 3. So yes, I can go. But can I go to 8? We can't because the difference exceeds. So it's overshooting. So what's the maximum I can go from 1? I can cover all of these, right? So the furthest node that I can go to is 4. So if this is the farthest node, it means all of the nodes in between are reachable. So I want to check in one jump, what's the farthest node I can go without breaking the max difference rule. So that is the thing we are doing here, that for every node we need to check now. That's why we have this left pointer, and initially our right is 0. And what we do is we iterate left until the size of the array, sorted array. Now what we do is we check if, we can cover the, next element. If yes, we increment right. And we hop until this is true. So, and then we say that from here, this is the farthest I can go up until right. Fine. So, yeah, this is how it is. And when right, overseats, we will know that, our we cannot go any further. So any which ways, then we always check from right plus one. Okay, now what we do is, we have this super jump cheat sheet. So this is basically a DP which will store, let's say I want to make so what it does is, from we have this DP which stores power and node. So these are the nodes and these are the powers. So it stores up until power 60. I meant to say 17, but since we are starting from 0. So, yeah, by 16, the reason is that 2 to the power 17 is 131072. And the maximum n that we have is 10 to the power 5. So 17 can hold at max steps. So that is why. So then we see that when we take 2 to the power 0 jump, which is 1 jump, from node 0, where do we land? From node 1, where do we land in 1 jump? And from same we calculate. Like, for example, if I want to calculate this value, what does this mean? Let's say from node 0, we take 2 to the power 1 jump, 2 jumps. So where do we, go? Where do we land here if we take 2 jumps? So this is our DP, which will store all the values. Now, just notice one thing. To make 2 jump, can we take 2 smaller 1 jumps? Why? Let's say how. Let's say from node 0, um, let's what are we trying to do? From node 0, we are trying to take 2 jumps. So can we do like this? From node 0, can we take 1 jump? And wherever we reach, can we take another jump from there? So will that be equal to 2 jumps? Correct? So that is what we are trying to derive here. If from node 0, which is the same, I, if we take power minus 1 jump, so wherever we land, and from there we take another jump, another power minus 1 jump. So then we know that, we can find the values here. So we can quickly fill this cheat sheet. So what are we trying to do is, we've created this dynamic programming array, DP array. It's a 2D array. Now this is base case, which is 0 jump, like 2 to the power 0 jump, which is 1 jump, which was basically calculated by next jump only. So we just initialize all the values here. Now what are we going to do is, for up until every power, we're going to iterate for every I, which is every node, and we're going to check if we take power minus 1. I mean, the same thing here. If you want to make 2 jumps, we need to take 2 1 jumps, right? So power minus II. So let's say this tells us that, oh, this is the place where we can reach the farthest. Then from there again, if we take that same, if we again take a jump, we are going to get our answer. So that is what we've done here. Fine. So then what we do is, now we simply go to the queries and we see how do we get the answer. We have pre-computed everything. Now what we will do is, so we check every, we check every query. And this is our, what does the query say? We have this U and V, correct? So this is my start U, original U, and this is my V. Now what do I do? If let's say, if my start and original is same, I mean, if my U and V same, is there a distance in, can I go from the same node? Yes, we can go. In how many steps can we go? In 0 steps. We are exactly there, right? So that's why we assign 0 here and we continue. Else what we do is, we're going to have U and V from the mapped index. So let's say this is my start. So I'm trying to get my U from this mapped index, right? So where is this in my sorted array? So this becomes our U and V because we've sorted the array, right? So in sorted array, where is my start and target? So we get U and V. Now we see if they are connected. If they're not connected, it means that there is no path and we've already initialized our array to -1. So we filled our array with -1. So we continue. Else what we do is we want to move forward always. So that is why whatever is the shortest value will be in U and whatever is the farthest value will be in V. So we've solved it here if there is a mismatch in the order. U should be less than V. So now what we do is less than equal to case will be handled here, right? So now what we do is we calculate how many hops did we make. And what's my current, U? I mean, we start from U and this is our current node. Now what we do is instead of, making one step at a time, we see what's the maximum step we can take at any particular time. So what's the maximum? 2 to the power 60. Correct? So this power is 16 and we go until power is greater than equal to 0. So what we do is we check. Let's say if my current, like from U, if I take 16, 2 to the power 16 steps, where do I go? If I land less than equal to V, if I land somewhere less than equal to V, it means that I need to go more further, right? So then what we do is whatever is the node that we are landing, we assign it to current. And then we add those many hops. Why those many hops? See, we did a trick here, but we can't really go 2 to the power 16 hops at once. We'll go them one by one, right? So 1 and left shift bar will give me the number of hops, which is basically 2 to the power 16. This basically gives me 2 to the power 16. So we'll add it to the number of hops we have taken. So then we'll keep going up until, um, you know, wherever maximum possible value. Fine. So this is how our hops will continue. I mean, this loop will continue. After coming out of this loop, what will happen is that whenever we overshoot this V, we will we know that we'll keep on decrementing power, and we'll only keep adding hops up until we don't reach V. We don't land at V. Correct? Now what we do is we check if after a lot of hops, and this is like we don't run into cycles. So what happens is after executing this, if we could reach at our destination, it means simply we could take those number of hops and we would reach the destination, correct? So a result of I has that value. Else what happens is we are somewhat, you know, beyond our destination, but taking one step, that is taking the next jump, would actually make me reach my V. So then I add hops plus 1 to the result. Else there is no path, so there's -1, and we've already filled the result array with -1. So then we return result at the end. So coming to the time and space complexity, see, this is our result array, which let's say that we do not need to count the size of the result array. So this is our sorted nums, which is of size n cross 2. So this is a space that we are taking up here. This loop runs for big O of n times. This sorting takes big O of n log n. This loop runs for big O of n time. And this loop also runs for big O of n time. So then in here, what happens is this will be less than n log n. And so in here, what happens is our right is a variable which is not local to this for loop function. So it is less than big O of n log n. N log n is the highest we've seen so far. Now this is linear, and this is big O of n log n. And what is log n here? It is 17. So it eventually reduces down to big O of n. And then this is basically big O of q. And this this thing is basically log n. So the total time complexity that we are getting is big O of n log n for sorting plus q log n, number of queries. So yeah, this is the time and space complexity. So if I just sum it up down, reduce it here, it would be n plus q log n. And n plus q can go in the brackets. So this is a time complexity. Coming to the space complexity, the dp holds, this dp holds power into node. So let's say we have n nodes and the power can go maximum up to 70, 16. So 0 to 16, so 17. So space is eventually, we can say big O of n log n. And what's my log n? It's actually 17. So that is for, the DP sheet. So we can say big O of n log n, or we can say n cross 17, which could also be reduced down to big O of n. Extra space. And obviously for we have some sorted array. So exactly this will also take n cross 2, which reduces down to big O of n. Then we have mapped index. This is again big O of n. Then we have connected components big O of n. This is also linear space. And yeah, this is the maximum space that we are going to, the maximum space that can be taken is via this DP. So that is the thing here. And obviously, while sorting, there would be auxiliary space. So I'm not, counting that. So it would usually be log in stack space used by our algorithm. So anyways, that was it from my end. Thank you.